In the name of God, I'm HEC-RAS, and in this part, we are going to talk about stable channel design in HEC-RAS 1D model. As you know, one of the most important issues in river engineering projects is the calculation of stable width and slope. Because performing the river protection measures without considering the stability factor can lead to erosion or sedimentation through the study reach. It is so important in regions in which the rivers crossing through a city or village or agricultural areas. Therefore, in this part of this course, we want to explain more about stable channel design in HEC-RAS model. Okay, first of all, I open my HEC-RAS model and my previous project about compound channel. In order to calculate the stable channel parameters, you should go to the hydraulic design section, and in this window go to the type menu and select stable channel design. Okay, as you can see in this window, there are three different methods, including Copeland, regime, and Tractive force. Which of them has special parameters and inputs that differ to each other. Okay, before going to model stable channel design parameters using different methods, let me check the structure and formula of these methods, or the philosophy of these methods. Okay, as I said, HEC-RAS estimate stable channel parameters using three different methods. The first one is Copeland method. The Copeland method is a stable channel design formula or method was developed by Dr. Ronald Copeland at the Waterways Experiment Station, or WES, for using STEM software package. This approach is primarily analytical on foundation of empirically derived equation, and it uses the sediment discharge and flow prediction methods of Brownlee equation to ultimately solve for stable depths and slope. First of all, Copeland method requires sediment concentration over the bed. In HEC-RAS, you can use this method, or HEC-RAS automatically use this method for estimation of sediment concentration, which is the function of FHG, grain-related fluid number, FHGO, critical grain-related fluid number, S, the bed slope, R, B, and D, 50, bed hydro radius, and median grain size. Okay, in HEC-RAS you can use you can enter your sediment concentration, or let HEC-RAS to calculate these important options, and FHG and other parameters can be calculated using these equation. For example, FHGO can be calculated using this equation, which depends on some formula at the below formula. After the calculation of sediment concentration, HEC-RAS use Brownlee's resistance equation for estimation of stability parameters. For example, for both upper regime and lower regime, HEC-RAS uses two different methods. I mean, upper regime for flows have fluid number lower than 1, and upper regime is related to flows with the fluid number higher 1, and lower regime is related to flows have fluid number lower than 1. And after calculation of these parameters. The model related these formula to depths, widths, and stable slope of channel. Okay, finally, using this equation, model calculate the area of a stable channel, and using the flow rate, it calculates the channel width and stable width and slope width. One of the most valuable of Copeland method is that this method calculates about 20 combination of slope and width or slope and depth parameters. And in the HEC-RAS, using this equation, it creates a different stable width for different fluid discharges. And finally, in HEC-RAS model, you can see figures like this, which represents the relation between stable slope and stable width. When you choose a base width and a slope higher than this curve, the river or the channel starts to degradation or erosion. And when you select lower values, lower this curve, it means that your design is tend to aggregation or sedimentation. The best values must be selected on this curve. In other words, you can you have several alternatives or options for selecting stable width and stable slope. Okay, this is for slope and width, and the other curve is for slope and depth. Suggested design discharges that may represent the channel forming discharge are 2-year frequency flood for perennial streams, 10-year frequency flood ephemeral streams, bankful discharge, and effective discharge. Okay, this method or Copeland method is one of the best methods for calculating or estimation of stability parameters, because it offers about 20 combination for stability parameters, while other methods only calculate one value for each stable parameters. Okay, this data set and applicability of Copeland methods for lab and field studies. And this is suggested input restrictions for Copeland method. For example, the method for sand only restriction for D50 varies between 0.02 and 6.6, and median grain size in feet dimension. Another method is regime methods. The regime method for a stable channel originated from irrigation design studies in Pakistan and India, and is based on set of empirically derived equations which typically solve for depths, width, and slope as a function of discharge and grain size. To be considered in regime or equilibrium, transport of sediment is allowed as long as there is no net annual score or deposition in the channel. The regime method is applicable to large-scale irrigation system with wide range of discharges, because regime equations are purely empirical and based on field observation, and therefore using this method for natural rivers cannot lead to good results. Okay, also the Blanche regime method is one of the best methods and is used in HEC-RAS instead of Lacey or other regime methods. In a Blanche method, the three regime equations are used for base, depth, and slope stability. And you can see each formula have some variables and some inputs. For example, for stable width, you should calculate parameters such as FB, FS, and Q is the channel forming discharge, and FB and FS is the bed factor and side factor. FB can be calculated using this equation, and FS for different banks varies between 0.1 to 0.3. For example, for friable banks, for silty clay loamy banks, it's equal to 0.2, and for tough clay banks, it equals to 0.3. Okay, after calculating FB and FS, you can easily calculate stable width and stable depth. Also, for calculation of stable slope, you need FB, stable width, stable depth, and sediment concentration, which is calculated in the previous section. And new is the kinematic viscosity. For example, for water is equal to 10 exponent to -6. Okay, regime method has different restrictions. For example, including the size of channel behaves as if hydraulically smooth. Bed width exceeds 3 times to depth. Side slope are consistent with those of cohesive nature. Discharge are steady. Sediment load is steady. Subcritical flow. Sediment size is small compared with depths of water and other restrictions. Therefore, these circumstances seem very confining, and in reality, no one channel or canal can claim to behave strictly this manner. However, if the channel can adequately approximate by these conditions without deviating significantly from its true nature, the regime equation may be applicable. But my experience shows that regime method is not applied for natural rivers, and I use a Copeland method in most reality project because it offers me about 20 combinations of widths and depths, and I have different options to choose in real projects. Finally, the third method is the tractive force. It's a completely analytical method and completely differ from regime and Copeland method. Tractive force is based on solving shear stress formula and uses the initiation of motion using, for example, shields or lane or user initiation of motion parameters. For example, it also calls shear stress or drag force and can be represented as tau 0 equal to gamma RS. And for initiation of motion, the tractive force uses 3 different methods. For example, the first one is lane method. Lane conducted experiments on canals in San Luis Valley of Colorado to develop a method for predicting the critical shear stress. And you can find this equation for critical depth is related to the D 50-70%, or linearity related to the diameter of particle size of 57%. And Shields method has historically been much more widely used to determine the initiation of motion. Shields develop a relationship between the shear Reynolds number RE and the critical mobility parameter. and in this equation you can see the Reynolds number, the U star or shear velocity, and finally the critical mobility parameter can be calculated using this formula, toe critical and other input parameters. And using this figure, that's a Shields diagram, you can find or calculate the initiation of motion or critical shear stress. Okay, let's go back to the HEC-RAS and calculate the stable channel parameters using different methods. Okay, first of all, you should open HEC-RAS, and like the previous study or projects, I opened compound channel projects, and I want to calculate stability parameter in this project. Okay, click on HD or perform hydraulic design computation icon in the main window of HEC-RAS, and you can see this figure. In the type menu, select stable channel design. Okay, let's calculate stability parameters using Copeland, which is an analytical and empirical based method for stable channel design calculation. Okay, first of all, require input parameters. You should enter discharge value for calculation. Okay, I want to use 50 cubic meter per second for discharge. As I said, you can use in real river this method, and discharge can be used 2-year frequency flood or 10 frequency flood, 10 return period or 2 return period. Okay, a specific gravity. You can use the sedimentation specific gravity for your grain particles, and in natural rivers we use this number for specific gravity, which is suitable for sand and gravel bed particles. Okay, the other parameters we should enter is the gradation information. Gradation information is about the particle size at different finer percent. For example, you should have the bed material gradation using observed data set. For example, I want to enter 20 millimeter for B84, 40 millimeter for B50, and finally enter 8 millimeter for B16. Okay, and then press OK. This optional input does not mandatory input data, and as you can see, they are optional. Valley slope, the slope of a river bed, and medium channel width. We don't enter these parameters and let HEC-RAS to estimate med channel width. And the default regime can be choose as upper regime or lower regime. The default value is lower regime. Okay, the other information is about bank input, and you should enter information about side slope and Manning coefficient roughness. Okay, in this project, I assume that my channel side slope is about 1.5, and for the right side is about 1.5, and Manning roughness coefficient is about 0.04, and this is for the right side. Okay, the final Important input parameters include inflow sediment. As I said before, you can enter your flow sediment concentration manually if you have observed data set, and you measure the inflow sediment concentration. You can enter that value in this section. If you don't have any data or any sense about sedimentation concentration value, you can let HEC-RAS to calculate the inflow sedimentation concentration. Okay, HEC-RAS needs some input variable and parameter to calculate this important parameter. For example, supply reach bottom width. You should enter the channel or river bottom width at the upstream parts of the study area. For example, if you want to model a river, for a stable channel for a river, you should enter the river width at the upstream of this part. Okay, in this part, I want to enter 5 meter for bottom width, and supply reach bank is the bank height for upper cross section of my or upstream parts of my study reach. And in this section, I want to enter 2 meter for height. Let me show you. Assume that the channel width and bank height like the cross-section shape like this. Okay, this is bank height and this is bottom width. Okay, supply energy slope, you can use the bed slope for energy slope. In this example, I want to enter this value. And for side slope and n Manning coefficient values, you should enter the previous values I entered in this section. Okay, this is value for Manning. Also, you can use a Manning or Strickler equation. When you click Strickler, the HEC-RAS use Strickler equation for estimation of bed resistance. Okay, I change it to Manning equation and press OK, and all important inputs is entered, and you can see the compute button has appeared, and you can click on apply and then click on compute, and you can see that this window and you can see the sediment concentration, which is calculated using HEC-RAS, is about 1.50 ppm. Okay, I select OK, and you can see the stable channel for a specific depth and width. In order to better presentation of stability, stable channel design parameter, you should click on stability curve 1. This is the relationship between stability slope and base width. As you can see, when I click on the curve, the value of stable width and stable slope is appeared. As I told you before, when you select a base width of about 30 foot and a slope of 0.0018, my channel started to erosion, and this is not good for river engineering studies. And when you select width and slope lower this curve, this means that your channel or your rivers start to sedimentation. Therefore, the best values for a stable channel design must be selected on this stability curve. In the table, you can see 20 values for base, width, and for slope. It means that you have different choices for estimation of stable width and stable slope. For example, in some areas we have a small width. You should change the stable width. For example, for higher width, we use higher value for stable, and for lower stable width we use higher. For lower value of base width we use higher value for slope, stable slope width. Okay, and then you can select on a stability curve 2. This is the relationship between depth and slope, and for selecting appropriate stability parameter, you should click on the curve to find the stability parameter. For example, in this case, for 1.1 feet stable depth, you should use this value for stable slope. Okay, by combining these figures, you can find all values. For example, if you have the limitations of about a slope value, you can select slope and find the stable width, and therefore extend this figure. For example, this value is for a slope and this value is x. Okay, using both a figure, you can find a better choice for stable parameters. Okay, the next method is the regime. The regime method, as I said, is apply and develop for irrigation channels, and in most times it's not lead to applicable or suitable results in natural rivers. Okay, let me to enter the previous values for regime. D50, let me check. Okay, this is for D50. Sediment concentration is about this value. Temperature, the natural temperature about 20. Temperature site factor FAS, as I said, for different materials it varies between these value, and 0.2 represent that your channel material is silty or clay or loamy banks. Okay, apply and press compute. As you can see, the regime depth is about regime width and regime slope. Okay, the regime width I think is higher than that of in Copeland method. Let me check again. Copeland method, as you can see, in Copeland method it varies between about 5 to 50. However, in this case the value are applicable, but for regime depth it's not a good value, because you can't create or protect a river using only these small value depths. Regime slope or stable slope and regime width a little bit okay, but regime depth is not so good. For natural or real projects. Okay. The second one is a tractive force. For tractive force also you should enter discharge enter 50 cubic meter per second, temperature set to 20 centigrade, and angle of repose for side left, right side, and bed. And this is the angle of response of sediment on the left side. For example, I assume that my channel side angle of repose is about 30 degree, and side slope is about 1.5, and the Manning value is about 0.04 for right side, left side, and bed side. Okay, as I investigated in HEC-RAS manual for estimation of initiation of motion, HEC-RAS uses 3 different methods: lane, shields, and user-defined mobility factor. Okay, first of all, we use lane method. Lane method requires the material size of 50%. Okay, I will enter the values of, let me check the gradation. Okay, D84 about 20. These values must be extracted using observed or measured data sets. Okay, I click apply and press compute. Okay, let me check the error value. The side slope angle is greater than the angle of repose. Side slope must be at least this value. Okay, let me check. Let me enter higher value. Okay, the other error or warning says that too many empty or unblended input boxes. In tractive force, you should enter one of these value, and HEC-RAS calculates the other both parameters. For example, I want to enter the depth value. I enter depth 2 meters, and HEC-RAS automatically calculates stable width and stable slope. As you can see, the stable slope is very low, lower than that of in regime and Copeland method. As you can see, the stability slope in Copeland method varies between these values, while for tractive force it is very low value, and it may be in real project it can be used for natural rivers. Okay, at the second part you can use slope. For example, if you have the restriction or limitation about a slope, you can use a slope and let HEC-RAS to calculate both the and depth and width parameters. Okay, you can see the depth value is very low value and it's not applicable for natural rivers, and the stable width is very large, and we are not allowed to use such these values in natural rivers. Okay, as an overall, I think and I experienced that Copeland method is the best one in HEC-RAS compared to regime and tractive force, and recommend you to use this method in real project and natural rivers instead of using these methods, because these methods can be used or suitable for irrigation channels or man-made channels. Okay, the other method for initiation of motion is the Shields method. In the Shields method, you should enter D50 particle size. millimeter for D50, and again I entered my restriction about or limitation about depths and press compute. Okay, the stable width is okay, and the stable slope okay, better than a lane method. And the second method is user-defined mobility. You should enter the theta critical for your method. In most and real projects, we use Shields method for estimation of critical shear stress for initiation of motion in most real projects. Okay. Okay, then choosing which of them is based on your limitation and your restriction of your project. If you have a limitation about a slope, you should enter the slope. If you have the limitation about depths, you should enter depths. And if you have limitations about width, you should enter width and let HEC-RAS to calculate both other parameters. And finally, you can copy this stable shape to your geometric data. You should press on copy XS to geometric data and copy this cross section to your desired river station. For example, in this figure, I want to copy the stable channel shape to this cross section. You can enter the river station and copy the calculated stability cross section to your project. Okay, I hope this course or this part is useful for you, and just have a good time.